So in the last section we saw about complex numbers differentiation. Now let's see complex integration. Well, okay. Now consider a continuous function f of z of the complex variable z, which is x plus iy, defined at all points of curve C. So let's consider basically a curve C, okay, which passes through endpoints A and B. Okay, and now I'm dividing this curve into n small n number of points. Okay, so this is basically written as z0. This is p1 of z1, and the p point is basically called as pn zn. So basically this is, so you have defined a curve which have endpoints a and b, okay, and you have a continuous function f of z which is defined at all the points in this region. Okay, so f of z has a value at a and at all the n points, n parts which you have defined on this curve. Okay, so now let's call delta zi be zi minus 1 and zeta I be any point on the arc pi minus 1 pi. So if you let's say this is I minus 1 and this is I. Okay, so on this arc zeta be any point on this arc. Okay, so now f of zeta I delta zi. Okay, now this basically a function f of z, and I'm multiplying it with the difference in the complex numbers at I and I minus 1 point. Now this sum, if I do, I varies from 1 to n, that is for each part. If I sum all this, and as n tends to infinity, so we can say that the length of the chord delta zi basically approaches 0. Obviously when n you are divided into n infinite number of points, then delta zi will be vanished to 0. Okay, so then this becomes basically integral f of z dz. Okay, this becomes basically integration under the limit that as n approaches infinity, this becomes integral, and this is called the line integral of z. Line integral of f of z taken along C, taken along the curve C. That is how it is defined. So f of z can also be written as u plus iv, where u is a function of x comma y and v is a function of x comma y. So then I can write integral f of z dz as, now noting that, now this, so writing fz, noting that dz is dx plus I dy, so I can write integral fz to be u plus iv integral dx plus I dy, and this if I just simplify, I can write it as u dx minus v dy. Now iv and I dy will be I square v dy, which is minus 1. Okay, plus the imaginary terms I can write separately, which is v dx plus I u dy. Okay, so this will become integral c u dx minus v dy plus I integral c v dx plus u dy. Okay, so it basically, evaluation of line integral reduces to evaluating line integral of real functions. Okay, so that's what the point is. Evaluation of line integral is reduced to line integral of what? Line integral of a complex, remember this is integral f of z dz. So line integral of a complex function is reduced to evaluation of two integrals of two line integrals of real valued function. Real valued functions. Okay, so this is the point about line integral. Now let's solve one problem. Okay, prove that integral dz z minus a is 2 pi I. Okay, this is what we need to prove. And the second bit is this is the first bit. The second bit is integral c z minus a n dz is equal to 0, where n is any integer, n belongs to integer, and it's not equal to minus 1. Okay, so that's again. And where c he has defined is the circle represented by z minus a mod is equal to r. Okay, so we need to evaluate this. Okay, so let's do it. Okay, so for the first bit, what we need to do, so let's plot first c actually. Okay, so c is z minus a mod is equal to r. Okay, and so c minus z minus a is basically, obviously z minus a is a complex number which in the exponential form can be written like this, where r is the radius and theta varies from 0 to 2 pi. So this describes that this is an equation of circle with a as the center. Okay, okay, so the center is represented by the complex number a. Okay, and z is any point, z is is any point on the circle corresponds to complex number z, and so this becomes the radius r and this becomes the angle theta. So this is your curve c, which is represented like this. Okay, now I need to evaluate this as dz by z minus a. Okay, this along the curve. Okay, so let's substitute, let's evaluate in terms of polar coordinate instead of in Cartesian. Let's evaluate in polar coordinates. Okay, so now z is this, so dz is basically, if you just evaluate dz. Okay, so here a is constant, r is constant, so I can just write dz as r e power I theta into, so with respect to theta I'm evaluating, I mean differentiating, so I can write dz as I r theta. Okay, so just now uh, putting everything in terms of polar form, so z minus 1 is r e power I theta. So this now, no, so everything is, so the now the integrate, I mean the variable of integration is theta, so I can 0 to 2 pi. Now I can take out common, this is 0 to 2 pi integral theta, because this and this gets cancelled, so this is nothing but I into 2 pi, which is 2 pi I. So this is a simple proof. Only thing is, line integral of the function 1 by z minus a, you have just converted into, you have used the polar form, basically the exponential form. Okay, and found out the integral. So similarly, z minus a whole power n dz along a curve, so let's substitute z minus a as r e power I theta whole power n, and dz we have found out I r e power I theta d theta. Okay, okay, so here why you have differentiated with theta is because r is not varying. I mean, even if you theta r and theta different variables, r is not varying. Okay, r is constant. Okay, so this will become r power n e power n I theta to e power I theta d theta, and 0 to 2 pi is the integral. So this can be written as I, r is constant, so r into n, r power n into r will become r power n plus 1 is equal to 0 to 2 pi. This will be e power n plus 1 theta into I d theta. Okay, so now exponential I can just um, integrate e power theta is basically e power theta only by your internal derivative. Okay, so this here, so that's why the n can't be -1, because this will blow off, or this will become 1 by 0, something like 1 by 0. Okay, so I can write r power n plus 1, I gets cancelled, which is n power 1 n plus 1. Okay, and then now just substitute 2 pi, so e power n plus 1 into 2 pi I minus e power 0. Okay, so this will basically become now now e power 2 pi n plus 1 I we need to evaluate. So this is nothing but cos 2 pi n plus 1 theta, because e power I theta is basically cos theta plus I sin theta. So 2 pi n plus 1 plus I sin 2 pi n plus 1. Now n plus 1 is an integer, so anything, so basically these are integer multiples of 2 pi, so cos and sin are 0. Okay, cos and sin are 0. So cos 0 plus I sin 0, cos 0 plus I sin 0 will be 1 plus I into 0, which is 1. So e power 2 pi n plus 1 is 1. So this can be written as r power n plus 1 by n plus 1 into, this is 1 minus 1, and this is 0. So when n is not equal to -1, this becomes 0. So this is just, I mean, how to convert line integral, complex line integrals into just using the polar form. We can just easily evaluate those line integrals. So now we come to an important theorem which helps in evaluating various integral forms of f of z. Okay, and it's an important theorem in complex integration. So what it says is, if f of z is analytic function. So remember what is analytic, we just did a section on that before, just some time back. What is analytic function? Analytic function is one which possesses derivative at all points. Okay, so if it is an analytic function at each point within and on a closed curve, within and on a closed curve C, then you can say that integral f of z dz is 0. That is what we can say. Integral f of z dz is 0. So only thing is, integral f of z dz can be said to be 0 if we have a closed curve C and f of z is analytic within the curve. So that's it. So if you have said something like this, okay, this is a closed curve and everywhere here f of z is analytic, then you can say that integral f of z dz is 0. So this is a very important result. Okay, and now the extension of this theorem, there is one more extension, important result, which is Cauchy's integral formula. So let me just write it down what it means. When f of z is analytic within and on a closed curve, and if A is any point on C, any point within C actually. So f of z is analytic within and on a closed curve C, and A is any point within C, then within C or on C, then you can write f of A is 1 by 2 pi I integral C f of z by z minus A dz. What it means is, if you can evaluate f of A, or basically you can evaluate integral f of z by z minus A dz by something like this. Okay, So this is just an extension of Cauchy's theorem. We are not going to prove it, but we'll try to apply this in solving some integration problems of complex numbers. So you have to note here that f of z by z minus a is not analytic. Means is analytic, but it's not analytic except, I mean, it's analytic but except at z is equal to a, because once z is equal to a, this becomes blow up, I mean it blows up. So is analytic at all points except 0. Otherwise what would happen? Otherwise the integral would have been g. That's what this says, right? If f of z is analytic at each point within and on a closed loop. So this is analytic everywhere, because f of z is analytic, and f of z by z minus a will also be analytic at all points except at z is equal to a. Okay, otherwise what will happen? The integral would be 0. That's what the first result says. Okay, so something of this form you can easily evaluate using this Cauchy's integral formula. Okay, so now let's solve some examples using this Cauchy's integral formula. Okay, so evaluate integral z square minus z plus 1 by z minus 1 dz, where C is a circle. Okay, and in the first case C is a circle with radius 1 and origin as the center. In the second case C is a circle with radius half and center of origin. Okay, so let's evaluate for all the cases. Okay, so f of z is z square plus z plus 1. Okay, and we see that this is analytic everywhere within a circle. Mod z is equal to 1. So mod z, okay, oh sorry, let me draw it correctly. So this is the origin. Okay, this is the origin, and z is any point, and the radius is 1. So that's why it's mod z is equal to 1. Okay, so everywhere this is analytic. I mean, this is a continuous polynomial function in z, so it has to be, I mean, there's no problem in the differentiation. Okay, I mean every point the derivative will exist, and a is equal to 1 because this is z minus a, so a is equal to 1, and this lies on the circle. Okay, this lies on the circle. So now, so we can readily use this formula, which says that integral f of z minus a dz, so it satisfies everything. F of z is analytic within and on the closed curve z, and also also the a is equal to 1 lies on the circle. Okay, so this satisfies everything. So this becomes basically 2 pi I f of a. Okay, so which will be 2 pi I f of a is like basically substituting 1 at the place of z in this. So 2 pi I will be basically 1 minus 1 plus 1. So it is 2 pi I is the result. Okay, so this is the result for the a bit. So let's evaluate the second case where mod z, the curve has the radius 1 by 2. Okay, is the radius, and point z is here. Now integral z square minus z plus 1 by z minus 1 dz. So comparing with this form f of z by z minus a, okay, we come to know that a is 1 here. So a is outside the circle represented by mod z is equal to half. So when a is outside, you can say that f of z by z minus a is analytic. This entire function is analytic everywhere within and on circle mod z is equal to half. So when this is analytic, so we know that integral gz dz and when gz is analytic everywhere within and on the curve, this value is 0. So the value of the present integral is 0 everywhere. I mean, is 0. That's the thing. This is by Cauchy's theorem. That's what we have used by Cauchy's theorem. Okay. So these are things. Simply we can use these two theorems extension. If the entire function is analytic, then integral f of z dz, if it's analytic within and on the curve C, then the integral value is 0. The line integral value is 0. And if then, and also there is an extension for the Cauchy's theorem, which is your Cauchy's integral formula, which says that integral f of z by z minus a dz such that f of z is basically 2 pi I into f of a, where a is any point within or on the curve, right? Such that your f of z by z minus a is not analytic at z is equal to a. So that's the idea. Okay. So now let's solve another problem and describing all these principles. So let's see some other problem. Let's evaluate integral e power 2z by z minus 1 z minus 2 dz, where C is circle such that mod z is equal to 3. Okay, C is a circle such that mod z is equal to 3. So z is basically something like this. Okay, mod z is equal to 3. The radius is 3, so any point on the circle is z. Okay, so now here I can use partial fraction to just keep this in this form. So comparing with the numerator, it is a z minus 2 plus b z minus 1. This has to be 1. So the z terms a plus b z minus 2a minus b has to be 1. So basically there is no z term on the left hand side, so a plus b has to be 0, minus 2a minus b has to be 1. So a is minus 1, a is minus b, and if we substitute it here, you will get plus 2b minus b is equal to 1, implies b is equal to 1, and b is equal to 1, a is minus 1. So the entire thing can be written as z minus 1 minus z minus 2. Okay, so now let's see how this integral looks like. This I can write integral 2z by z minus 1 dz minus integral c e power 2z by z minus 2 dz. Okay, so now z mod z is 3. So a here, comparing this, a is 1, comparing in this form, standard form f of z by z minus a dz. So comparing with that, a is 1 and a is 2. So a is inside the, in both cases, a is inside the curve C. Okay, so we can just apply the Cauchy's integral formula, because that's the condition for it. A shouldn't be outside, a has to be within or on the curve. So this will be f of a 2 pi I into f of a. So f of 1 here minus 2 pi I f of 2. So f of z is basically e power 2z. Okay, so this is 2 pi I, f of 1 is e power 2 minus 2 pi I e power. Now here a is 2, so this is, let me see what mistake we have done. Well, a is minus 1 here and b is plus 1. That's the thing. A is minus 1, b is plus 1. Okay, so this is minus, this is plus, this is plus, this is minus. So f of 2 you have to substitute, this is e power 4. So this you can write 2 pi I, you can take out common, which is e power 4 minus e square. So this is the value of the integral 2 pi I e power 4 minus e square. So just using a simple Cauchy integral formula, we can just evaluate complex integrals of this form. So now let's see, evaluate another integral. Let's see another problem. Evaluate integral c cos pi z by z square minus 1 dz around a rectangle with vertices 2 plus or minus I minus 2 plus or minus I. Okay, so we have to evaluate this around a rectangle. So basically it's a closed curve. So let's first plot this rectangle in the argand plane. Okay, so 2 plus I lies somewhere here, 2 minus I will lie somewhere here, minus 2 plus I will lie somewhere here, and minus 2 minus I lies somewhere here. Okay, so if I join these two, basically becomes, if I just close this curve joining all these 4 points, it basically becomes a rectangle joining these 4 points. So this is a straight line. Okay, okay, so basically just to redraw it, the curve is something like this. Okay, where this is 2 minus I, this is 2 plus I, this is minus 2 plus I, and this is minus 2 minus I. Okay, so this is a closed curve. Okay, and you have to evaluate your the integral along this closed curve. Okay, so first you have 1 by z square minus 1, so this can be written as 1 by z plus 1 into z minus 1. So let me write in this way, a plus b by z minus 1. Okay, and then let me find out a and b. So this I can write a into z minus 1 plus b into z plus 1. So comparing z terms, a plus b has to be equal to 0. Comparing z terms, and comparing the constant terms, it is minus a plus b has to be 1. Okay, so when a is equal to minus b, so a is equal to minus b from the first, and then when you substitute here, it becomes b, you will get half, and a as minus half. So just substituting the everything in the integral back, I'll get a which is minus half by z square minus 1, b which is half by this is z plus 1, and this is z minus 1. So this you have cos pi z dz. So this can be written as plus half integral c cos pi z by z minus 1. Basically this part I am writing first, and then so this is integral dz, then integral c cos pi z by z plus 1 I am writing into dz. Okay, so this is half. Okay, so now this here a is what, a is 1 here, and here a is minus 1. Now both of them lies, well, a is equal to plus 1 will lie somewhere here, a is equal to minus 1 will lie somewhere here. So that is with, so point a is within the closed curve or closed curve C, right, within the closed curve which is a rectangle. Okay, so I can use the Cauchy's integral formula. So this becomes 2 pi I f of 1 minus 2 pi I f of minus 1. So this is half 2 pi I f of 1 means f of z is cos pi z. So this will be cos pi 1 minus 2 pi I cos pi minus 1. So 2 pi I cos pi is minus 1, cos 1/8 is minus 1, and here minus 2 pi I cos minus pi or cos pi, both are same, so this becomes minus 1. Okay, so this value is basically half minus 2 pi I plus 2 pi I, so which is nothing but 0. Okay, so this is how, I mean, we have seen some 3 to 4 examples on the Cauchy's integral and Cauchy's formula. So the basic idea is how to solve complex integrals, I mean complex integrals, how to evaluate complex integrals which are basically having complex numbers. So in this section we have seen what is complex integration, how to evaluate line integrals of complex numbers, complex functions basically using Cauchy's theorem and Cauchy's integral theorem, Cauchy's integral formula. So let's see now two important series of complex numbers, the Taylor series and the Lorentz series. So let's begin with the Taylor series. So what it says that if f of z is analytic inside a circle C, remember it's not any closed curve, it's a circle inside a circle C. If f of z is analytic and the circle center is A, then for z inside C you can write f of z is f of A plus f dash A z minus A plus f double dash A by 2 factorial to z minus A whole square plus so on. So this is just, it is just similar to your real number Taylor series. Okay, so only thing is you have a circle here which is represented by C and A is the center. So what he says is f of z is any function which is analytic within inside this circle. Then for any z within inside C, any z, you can write f of z, you can always express f of z with respect, say you know f of A and the derivatives of f of A, then you can express f of z as in terms of f of A and the derivatives of f of A in terms of like this. So this is your Taylor series. So let's solve one problem. Okay, find the Taylor expansion of f of z is equal to 1 by z plus 1 whole square about the point z is equal to minus I. So this is what we need to find. Now to expand f of z about z is equal to minus I, that is in the powers of z plus I. So let's put z plus I as t. Okay, so now f of z will basically become 1 by t minus I plus 1 whole square. Okay, so this we need to write properly. How do we write this is, well, I have to write in the powers of, I mean about the I. Okay, in the powers of 1 minus I, so I can write this, I can express as 1 minus I. Okay, let's take 1 plus 1 minus I common, so this will become 1, I mean 1 minus I common, so this entire thing becomes 1, then plus t by 1 minus I whole square. I can write this, I can always write, and this I can write 1 e power minus 2 by 1 plus t by 1 minus I whole power minus 2. Okay, so now we use binomial theorem. binomial theorem to expand all this, and this will become I by 2 1 minus 2t by 1 minus I. Okay, so 1 minus I whole power minus 2 you can just expand. Okay, and similarly you can expand this also. So this will become 3t square by 1 minus I whole square minus 4t cube by 1 minus I whole cube, so on. Okay, so this will become I by 2. I can write this as 1 plus, and now the general term can be written something like this: minus 1 to the power of n plus 1 minus 1 power of n plus 1, then you have z plus I. So I'm just substituting it back. I'm just putting t as again z plus I whole power n, and I'm just keeping it I only. Okay, so this is the general term, and so summation is from n is equal to 1 to infinity. Okay, so this is how I can expand f of z, which is 1 by z plus 1 whole square about z is equal to minus I can just expand. So only idea is you have to just bring it in this form so that you can expand by binomial theorem. Okay, or you can straight away use this also. Okay, so now let's see another series, which is Lorentz series of complex numbers. Okay, so what it says is f of z is analytic in the ring shaped region R, okay, bounded by two concentric circles C and C1 of radius R and R1, where R is greater than R1. Okay, and with center A, then for all z in the region R, I can write f of z as a0 plus a1 z minus a plus a2 z minus a whole square, so on, a power minus a minus 1 z minus a whole power minus 1 plus a minus 2 z minus a whole power minus 2. So these are just the similar terms. So here where the general term is written in this way, 1 by 2 pi I. So this is somewhat complex, but you can understand. F of t by t minus a whole power n plus 1 dt. This is the general term that's expressed in this. What is then tau? Tau is being any curve in R encircling C1. Okay, so what does this mean is that if you have two functions, this is C and this is C1, if you have two concentric circles C and C1 of radius R and R1 respectively, and the center is given by A, so radius of C is R and radius of C1 is R1, then within this region that is bounded by two concentric circle, you can expand f of z in this way. That's what it says, but this is quite complex. I mean, I don't know, hardly it is used. Okay, but it's there in the syllabus, so just we have mentioned it. So the basic idea is to obtain Taylor or Lorentz series, you have to simply expand f of z by binomial theorem. Okay, otherwise otherwise you have to find a power an general term an, which by complex integration will be quite complicated. Okay, finding out each the term. Even here also we don't find an. I mean, we just expand it by Lorentz series. I mean, we expand it using binomial theorem even for Lorentz series as well, the way we did for Taylor series. So that is the idea behind Taylor and Lorentz series. So in this section we have seen basics about complex integration, and then the series expansion of complex function, basically the Taylor series and the Lorentz series.